Hello guys, we're still on the topic of confidence interval. But for today's class, we'll be looking at the confidence interval when the population is normal, 1, 2, the population variance is unknown, and that is critical to note here, and 3, the sample size is small. And at this level, a small sample size is considered to be when n is less than 30. Now, based on statistical investigations carried out over a period of time and based on simulation of analysis, it was found that the best distribution that fits this scenario is what we call a T distribution. Now, there are some critical things to note about a T distribution. The T distribution has actually just one parameter, what is known as degrees of freedom. All right, and it is normally written as T is distributed over V, which is the number of degrees of freedom. Now, what is degrees of freedom, you may ask? The degrees of freedom is the amount of values that can vary without actually affecting the constraints of your distribution. And the symbol we normally use here is a common V. All right. Similarly to how my Z value is calculated, my T value is calculated in a similar manner. So we say that T is equal to x bar minus, and x bar of course is the sample mean minus mu, which is my population mean, over sigma hat. And what that means is that we're talking about the unbiased estimate of a standard deviation over the square root of n, which is your sample size. The number of degrees of freedom is actually n minus 1, where n is the sample size. So this is written as t is distributed over n minus 1. All right, and bear in mind that we normally represent the number of degrees of freedom using a common v, but it is calculated as n minus 1. Now here's my t distribution table. As you can see that this sums from negative infinity up to a point past 0, as you can see right here. Note also here I have p, which is my probability. These go right across the top here. And down here you have v equal 1. This is my degrees of freedom. So normally for me to find a t value, I would have to use my probability with my corresponding degree of freedom, which is on the left hand side here, which is what I'm indicating with my mouse. Once again, the probabilities are at the top, and what we have in here are my corresponding t values. Now this table can also work in reverse. So what if I'm using my degrees of freedom and I have my t values? I can find the probability that corresponds with that t value at the top of the table up here. Here's a typical question, guys. The mass in grams of a packet of biscuit of a particular brand follows a normal distribution with mean mu. 10 packets are chosen and their mass is noted. The data is summarized as follows. Before we look at the summary of the data, let us see if this has all the characteristics of the t distribution. So first of all, we know that there are 10 packets of biscuits, which means that the sample size is small, it's less than 30. Secondly, we are told that the distribution is normal, so two conditions have been met. Thirdly, we're not given the population variance, which means we're going to have to calculate an unbiased estimate. All right, so the population variance is unknown. So let us go down some more. The data has been summarized for me. We're told that the sum of x, which means when I add up all the packets, all the 10 packets of biscuits, I get 3,978.8 grams. And so important to note the unit here, which is grams. So let me start by finding the sample mean, which is x bar. Now x bar is equal to the sum of x over n. The sum of x has been done for us already. So it's 3,978.8 over 10. All right, and this breaks down to 397.88 grams. All right, we have that. Now we need a variance. Now, of course, we don't have the population variance, but we can calculate what is called an unbiased estimate. Now, the unbiased estimate is given by the formula sigma hat squared equal n over n minus 1 times s squared. Now, common s squared would actually be the sample variance. All right, so we're going to have to go back for the formula for that. Now, what's the formula for the sample variance? S squared equal the sum of x squared over n minus x bar squared. We know that x bar here is the sample mean. And the sum of x squared is given in the question as 1.5 million, and so on. So this goes over my sample size, which we know is 10 minus x bar squared. We found x bar already to be 398, well, 397.88. So minus 397.88 squared. Now you can simply just put all this inside of your. The sample variance becomes s squared equal 1.34. So now I'm going to have to find an unbiased estimate of the population variance with symbolic representation sigma hat squared, which we said was n over n minus 1. So it's going to be 10 over 9 times 1.34. So sigma hat squared, when I break this down, I actually get 1.49, which means I can get an unbiased estimate of the standard deviation. So I'm going to have sigma hat equal, I take the square root of that, and I get 1.22. We are found our unbiased estimate, so let us go back to our distribution. We must acknowledge that x is the mass in grams of a package of biscuits. You must define a distribution. We were told that the distribution is normal. We also acknowledge that. Now, bear in mind that we had found the conditions necessary to use the t-distribution here. So I'm going to have to talk about the number of degrees of freedom here. And v, which is what we use for the number of degrees of freedom, is equal to n minus 1, which is equal to 10 minus 1, which is equal to 9. All right. So it is written, it is a single parameter of the t-distribution written as follows. T is distributed over 9. All right. Now, we know it's a 95% confidence interval. So let us see what we get out of that. Let me set up my curve here. So here we go. So in the center here is 0. It is symmetrical about this area right here. So when I put in, let me put this in, we are saying that in here, this area under the curve is 0.95, or we say it's 95% of the curve. But the curve that we are using, it will come from negative infinity up to this point. So here's where I'm going to get my t value. This is my t value here. However, the curve will come from all the way down there. And since we have 95% here, we have 5% to share between these. So here we go. So this now is going to give me 2.5% down there, and the next 2.5% up here. All right. So when I combine those two, looking at the entire area here, I'm looking at 97.5%. So here, this entire here, the red area, including this yellow area here, is going to be 97.5%. All right, which gives me a probability of 0.975. So when I go to my table, I'm looking for 9 degrees of freedom, and I'm looking for an area of 0.975. From my question, we had 9 degrees of freedom, which is what I'm looking at the left hand side of the table here. The probability was 0.975, which is what we find at the top of the table. Now let us find the values that correspond to those two. So the 9 degrees of freedom, and with my probability being 0.975, the value that I'm seeing here in the table is 2.262. So as you saw from the table, t was equal to 2.262. Now that we have our t values, let us remind you of a few critical components that we need for this formula. X bar, which is 397.88, my sigma hat, which is an unbiased estimate of my population standard deviation, which is 1.22. N was 10. So all I have to do is fill in this formula. So I'm going to have mu is greater than 397.88 minus 2.262 times sigma hat, which is 1.22 over the square root of n. So it's the square root 397.88 plus, and notice basically we have the same thing on both sides, just that we are subtracting on the left, but we are adding on the right. So 3.398.88 times plus, sorry, 2.262 times 1.22 over the square root of 10. Now when you put this inside of your calculator, it breaks down to mu is greater than 397.007 to 3 decimal places, but is less than 398.753. So now I can actually write my statement. So I can say therefore the 95% confidence interval for mu is, that's of course mu is a population mean. And let me just round this off to probably 1 decimal place. So that's 397.0 grams to 398.8 grams. All right, and this is me writing it in terms of interval notation.